Hello, everyone. Welcome back for the final time. I was looking at the lecture notes, and actually we got quite a bit further than I thought we would yesterday, or sorry, Friday. So today is going to be a bit of a grab bag. We're going to wrap up the notes set, and I'm going to allude to things like Viterbi or turbo coding, sorry. And that's really all I have planned. I also released the solutions to problem set 6, and I graded most or all of problem set 2 and parts of problem set 3, so I'm progressively catching up. And I released problem set 7, which is not assigned, but is also available. The solutions are all available for you as well. So if all else fails, there's quite a large problem in problem set 7 that I wouldn't mind walking through with you, walking through my solution, just to give you another glimpse view of Viterbi decoding. So, but before I do that, I would like to know if there's anything you need me to cover, because we're not gonna. My agenda does not span 50 minutes today. Okay, so let's move over to the PowerPoint. And I'm on page 39. So the whole idea behind error correction coding is if you give me a set of bits, I'm going to do some stuff to those bits and then send more bits than you sent me to the next chain in the system, the next component in the chain. Now, the bits that I send don't have to be in the same order that you sent to me, right? We've talked about Hamming codes that put check bits in the middle of data bits. And you can take that to kind of an extreme by banking a whole bunch of data bits, encoding those into code bits, and then sending the code bits out in a completely different order than you would have otherwise sent them. And so one way to do that is called block interleaving. And the idea is that for codes that don't correct well in burst errors, that is, error correcting codes that have very few error correcting possibilities per code bit, per code word, a burst error is a death sentence because you were going to clobber most of the bits in a code word, which means that you can't hope to recover it. But even worse than that, you're probably going to decode it as something wrong, or you're going to say the most likely data sequence is the incorrect data sequence. So if your channel that you're trying to communicate the bits through is prone to burst errors, you have a couple of options. You could employ a more sophisticated encoding scheme like Reed-Solomon, which is more immune to burst errors than Hamming is. Or you could, I should say, there's nothing preventing you from doing both. You could send the code bits out such that neighboring code bits don't correspond to the same code word. Okay, and so the idea is, or one idea, is that we've got, so somewhere over here is the data to code bit generator. So this is your error correction code, data bits in, code bits out. And then those code bits are then shuffled into rows of this memory bank. Once one row fills up, then you fill the next row and the next, et cetera, et cetera. So you fill this memory bank by rows. And then once the memory bank is full, then you send the bits by columns. So once this is full, then this guy gets sent first, and then this sequence gets sent second, et cetera, et cetera. And so then on the receive end, you have the exact mirror of this. You would have an array, a memory array, that gets filled by columns, and then it gets exported by rows. Right? So you just do the exact reverse of what you're doing on the transmit side. The effect is that if there is ever a burst error, then that is more likely to clobber one of these columns, a single column. Come here now. So let's say that, I don't know, there's a burst error and these bits get flipped, right? It's bursty so that we're getting a lot of flips in a short span of time. And so if all of these gets flipped, that was, I don't know how many rows that would be, but that's a lot of bits. If we hadn't block interleaved, then that same number of bits would have clobbered, say, these. And this many errors in a single code word is unrecoverable, say. But if it's these that get flipped, then what happens when we go to export these back at the receiver? So at the receiver, the same table gets filled up this way, and then it gets exported this way. Every code word that comes out of this table is only going to have one bit that's flipped. So we've taken something that would otherwise, hamstring us, and we've diluted it across things that we can correct for. That's why someone would do block interleaving. Now it's not a silver bullet. In particular, if you have a burst that spans two columns, so say these and these all get corrupted. Actually, that would be fine too, because I haven't highlighted more than one thing in a row. But certainly, if this happened and this happened, then all of a sudden, this code word, once it gets exported, is going to have two errors, which, unless you're using a two-error correcting code, is going to give you a false positive, or it's going to decode to a data word that isn't the right one. Questions on this? All right. I think the rest of this slide set is going to have to be kind of a teaser for next quarter, basically. But what I do want to do, and before I let you go out of this class, is I would like to talk to you about this phrase, the Shannon limit. This is, it would be a shame for you to take a digital communications class in this day and age and not talk about the Shannon limit. Because everything that comes next, the stuff that we're going to talk about on 526, is going to be with the Shannon, like trying to achieve the so-called Shannon limit. So, and turbo coding is one such way of doing that. And the idea is that in turbo coding, you do convolutional encoding with an interleave, and then you decode them progressively, basically. So at the receiver here, you are running these through decoders independently. So you're taking every other symbol and sending it through these decoders, and then progressively de-interleaving them back together, which on its face sounds like a really confusing operation. But the idea is that you can improve your performance statistics by doing it this way. And I think I'm going to have to leave it at that. But the idea that there is a limit that we are trying to approach is actually, I think, a worthwhile topic to discuss today. So let me stop the PowerPoint and go to the whiteboard. Okay, so we're going to talk about, it's sometimes called capacity, it's sometimes called limit. But what I'd like to draw your attention back to is that we've talked about capacity of channels before. We called it the Nyquist capacity. And I want to juxtapose that with what could be justifiably called the Shannon capacity, also known as the Shannon coding limit. So the idea with the Nyquist capacity is for a noiseless channel, and that is key here, Nyquist says that you can mount at most 2 bits per cycle of the highest frequency content that you can pass through the channel. So this is the channel bandwidth, and this is the max data rate. So if I have a channel that's band limited to B hertz, then I can send at most 2 bits per B hertz, or on B hertz, and therefore I get 2 B bits per second capacity. Now, we had a different version of this that means that you could use for M-ary communication. So for channel alphabet, alphabet, tell you what, the end of the quarter can't really come, sorry. For a channel alphabet of size M, so think about this as the number of constellation points in your digital encoding scheme is M. This we can expand on our capacity to be 2 times the base 2 log of M times B. So this is the idea that we're not just limited to, if I have a bandwidth of B hertz, I'm not just limited to a single amplitude sinusoid at B hertz. I can try phase shifts, and I can try amplitude shifts, and they will all give me different ways to communicate bits at B hertz. And so you are mounting more bits per symbol, so that's why log 2M is going to increase your Nyquist capacity. Okay. So the idea behind the Shannon limit is, and it would be impossible, and at this point in the quarter, you know that I don't like to overgeneralize, but it would be impossible to overstate the importance of Claude Shannon to modern communications. Like, yeah, I think the first assignment in 526 is going to be to read his 1948 paper, which is like 3 pages long, and it started information theory. Like, it's crazy. But what the Shannon limit says is there is, for any given signal to noise ratio, so automatically we're talking about with noise, so what Shannon says is that for any signal to noise ratio, good, bad, anywhere in between, there exists a code or an encoding scheme such that information can be passed through the channel without error. So for any SNR, there exists an error correction code such that error-free communication exists. And so that is a crazy statement. Now, there are a couple of caveats here. First is that there's no guarantee on the code rate. So the code rate could be abysmal, right? If I have a very noisy channel and a very weak signal, I'm going to have to repeat the bits that I want to send a lot if I want to get them through eventually without error. Okay, so don't think that this means that we can have good codes for any SNR, but it does mean that there exists some codes. And the other it's the same. The probability of error-free communication goes to 1, or the probability of an uncorrected error goes to 0. That's right, Jack. The other big elephant in the room is the fact that this theorem proves that there exists such a code, but it doesn't tell you what it is. So not what it is or how to build it. So at first, I go back and forth on how awesome / frustrating this is, because this says that such a code exists, but I'm not going to tell you how to find it. And that's why the information theory and communication theory is still a field, is because people are still searching for these codes for various SNRs. So that's why the final module of this course was supposed to be capacity approaching codes, is because nowadays, within the last 10 years, people are developing codes that are approaching the Shannon capacity. Anyway, so he also gives a formula for what this capacity would be. So let's see here. Go back to blue. So the Shannon capacity scales with the bandwidth. So in that sense, it's very similar to Nyquist. But it has to incorporate the SNR. Otherwise, how the hell are you going to talk about that? So it looks like 1 plus the SNR. So Shannon says that for any SNR, there exists an error-correcting code such that I can expect to get CS bits per second error-free through the channel. Okay. I think there's an interesting view of this, especially if you kind of simplify this to be in the presence of additive white Gaussian noise. So assuming additive white Gaussian noise with power spectral density, say script n over 2, it's our favorite notation here, then the power of the signal and the power of the noise, we can write it more exactly. So we'll call the signal power P sub s, and then we're going to write that in relation to the noise power. Now, in white noise, the power spectral density is flat, and so the total noise power that your receiver sees scales with the bandwidth. That is, this thing is the power spectral density, the height of the rectangle times the width of the rectangle. That's the total power that your receiver sees. So it's interesting to me that the bandwidth shows up out here, but also shows up in the denominator over here. So this is, it is far more realistic, and I would venture more pessimistic than Nyquist, who says, give me more bandwidth, I'll give you more capacity. Shannon also says that, like, this is still an increasing function of bandwidth, but it's nowhere near as free-for-all as Nyquist. So actually, I want to bring up MATLAB, and I want to show you what this curve would look like, making some simplifying assumptions. But questions before I go off of the screen? All All right. So let's share MATLAB. Where'd you go? Okay, so no, I don't want to do symbolic. Let's do old-fashioned. Let's build a horizontal axis, so a bandwidth axis, and then the capacity looks like b dot times the base 2 log of 1 plus. I'm going to make up some numbers here. I'm going to say that the signal power is 1 and the power spectral density is 1. So then this works out to be 1 dot divided by b. So there will be a family of curves for different signal powers. So this is PS equal to 1, or at the very least, PS times 2 divided by script n. That all equals 1. That's my assumption here. So then if I plot B comma C, then we get the bandwidth on the horizontal and the capacity or the bit rate on the vertical. And this is what I mean by a much more pessimistic view, is that you can throw bandwidth at your problem if you need to get more data through, right? You aren't ever penalized for adding bandwidth, but I hope you can also see that you experience significantly diminishing returns. There is a regime where more bandwidth is going to help you a lot, but then there is also a regime in which every increment, every hertz that you add to your bandwidth really doesn't buy you that much in terms of data rate. Certainly not as it was for Nyquist, which this would be a straight line for Nyquist. So yeah, I think that this is, I mean, and people will say that like there are different views on this. Can I actually annotate this? I think I can. This is kind of your bandwidth limited regime. And then this is your SNR limited regime. Like, and by that I mean, if you had $10 to spend and you lie in the bandwidth limited regime, you should spend that $10 on increasing your bandwidth. If you have $10 to spend and you're currently in the SNR limited regime, you need to increase your SNR. That's where your money is best spent, is one way to look at that. Yeah, so the idea is that for every SNR, there's a family of these curves. And what you're after when you're designing a capacity approaching code is for a given bandwidth, so fix a B on this graph, you want your code rate to approach the resulting curve. Okay. Or said another way, how far away your code lies from that curve is a metric of how good it is and how good it could be. Or the distance from the ideal, it gives you a way to measure your code against other codes, which is actually a much more common way to look at this. Yeah. We are going to go into what's sometimes just called Shannon information theory a lot in 526, because that's where the majority of recent results in communication theory lie. It's in not thinking about the bit rate itself, but rather thinking about the information contained in the bits and how we can get a capacity approaching codes and whatnot. So that concludes the new stuff that I wanted you to learn in 416. As I said, there is a problem in problem set 7 that I have no problem with walking through the solution with you. But I don't want to bulldoze you into that. If you have questions on other subjects or other stuff that you need addressed.
I don't know if I want to, well, it might be a long question. I was just wondering how, there's probably a derivation on how he, how Shannon finds his equation. I was just wondering what he assumes, I guess, to create that equation for the bit rate. Because I'm just looking at the similarities between Nyquist and how how Nyquist uses negligence of noise to create that equation. I was wondering how that compares to? I don't know if that's a quick answer to ask.
Unfortunately not. The best proof I've seen of Shannon's theorem involves information theory, which means that we need to talk about information entropy and mutual information and all the stuff that I plan on teaching next quarter.
I'll get that answer then, I guess.
Okay. Stay tuned, I guess, is what I have to say about that.
Okay, thank you.
Yeah. Okay, so homework. Okay, so if you'd like to pull up the problem set number 7, I'm going to do problem 4. I'm going to walk you through my solution to problem 4. If you don't have it in front of you, I can share the screen right now and walk you through it together. Okay, so what we've got on our hands is a convolutional encoder, and I am going to walk you through how to build the state transition diagram, the trellis diagram, and we're going to encode a specific data word, and then we're going to try and implement Viterbi to decode this given received sense word is sometimes what it's called. So the convolutional encoder is a little bit more complex than the one we had before. It's still a 2-tap encoder, and it's still a 2-state encoder, but there's a few more XORs here, and there's also a feedback loop. So, but it is still, at the end of the day, it's still a convolutional encode. So, should we walk through what's going on here? All of these sums are meant to be XORs. And yeah, so I guess first things first, the data bit, one copy of it gets piped straight through to the code bits. So that one's the easy one. Another copy of the data bit gets fed back with a couple of XORs. So you XOR the previous state and the state prior to that. You XOR that with the current data bit, and that gets stored into state -1. That also gets XORed with the last state value, and that is your output, your second code bit. Okay. So let me switch over to the solutions to walk you through. But yeah, we're going to go through these 4, well, as much as I have time for. And you have access to this document as well.
Quick question, is V of K defined as the code word, or is it just some other part of the code word?
So for every turn of the crank, for every data bit that comes in, VK1 and VK2 get output as code bits.
Oh, code bits. Okay.
Yep.
Okay, that makes sense. Thank you.
Yeah, so here I've kind of translated or decrypted the diagram into an expression for the first code bit is the data bit. The second code bit actually works out to be the data bit XOR the previous data bit.
Is it 0 padded?
So yeah, we'll assume that the encoder starts in a 0 state, and if sending a finite string of data bits, we'll also assume that it will append enough zeros to pass all the data bits through. Yeah.
Gotcha.
Okay, so the first question is draw the state transition diagram. And so the reason that I spelled these out is because it's relevant given the state of the system, what each input bit creates. And so again, I lettered all of the states, all 4 of them. There are only 4 states because there's only 2 memory blocks. So if we assume that we start in state A, so that means we're sitting here in state A, which means that 0 and 0 are, by definition, the state of the system. Then the way to read this diagram on the left is if a 0 bit comes in, then the red stuff happens. If a 1 bit comes in, then the blue stuff happens. So if a 0 bit comes in, then everything is still 0. So we output a double 0 given an input of a 0 from state A. So state A goes to state A if a 0 bit comes in. If a 1 bit comes in, then that 1 bit pops straight out, but also another 1 bit comes out of the recursive encoder as well. So, and then the 1 bit comes to this state, so that means that we travel from state A to state C while outputting a double 1. Okay. From state B, which I defined to be a 0 and then a 1, we can transition either to state C or state A, depending on if a 0 or a 1 come in. And just to remind you, this notation, bit slash bit bit, bit in, bit out 1, bit out 2. This is the input, and these 2 are output bits. Which, and I want to stress, this is not the same as the state of the system, right? The input and the output are different than the state. The state is encoded by these 4 positions, which are themselves 2 bits, but they're not the output bits. Okay. Okay, so you do the same operation for each of the 4 possible states. So if we're in state C, which is 1, 0, then we can either jump to state D or state B, depending on what the input bit is. And if we're in state D, then we either cycle through state D by feeding in more 1s, or we jump to state B if we see a 0-bit input. All right, so once you've got the full state transition diagram, and I've just built them state by state, but if you put all those states together, you get the right-hand side here. The right-hand side of this diagram, if you smear it out across time, you get the trellis diagram on the left. So the way to read this is from state A, I go to state A if a 0-bit is input. So I'm taking this loop and I'm mapping it here. And then if I were in state A, I would again, so there's another option. I think I've omitted some things from this diagram for the sake of building it. But if I'm in state A, then I jump to state C if a 1-bit is input. So from state C, this diagram says I can either go to D or B. So D or B, based on if either a 0 or a 1 is input. And then from B, I can either transition to A or C, depending on if a 0 or 1 is input. So A if a 1 is input, and C if a 0 is input. And then to complete the picture, from state D, I can either cycle back to myself or jump to B. So this is cycling back to D, and this is jumping to B. So once you find yourself in any state, then this part of this picture tells you how you transition to any other state, right? So basically this orange blob gets copy pasted over and over and over again. Questions here? Okay, so that was parts A and B of the problem. in part C, we're given a specific data word. This is what, 10 bits long, and we're asked what code word does this map to. So strictly speaking, this is a 2-to-1 encoder, so we should expect 20 bits out. But because we're going to pad it with zeros to clear the data through, we're actually going to add, I think, 2 extra data bits, which means we'll end up adding 4 extra code bits. So 10 data bits gets us 24 code bits, I believe.
So I know I understand where you pad on before where you started the A state. How does the padding at the end necessarily work? Is that because, oh, that's just because we need those extra 2 to create the final bits in the data point. Okay.
Yeah, every data bit, quote unquote, lives in the system for 3 time steps. Its initial, and then 1 later, and then 1 after that, because it's a length 2 encoder. Okay. So yeah, in order to treat this bit the same as this bit, I need to act as if there's more stuff. But these I truly don't actually care about. I just need them to encode the final 0 with as much care as the first 0.
That makes sense. Thank you.
Mm-hmm. And yeah, so yeah, I think we've been using padding a little bit too much. There's the assumption that the system starts in a relaxed state, which is why the diagram starts in A. And then there is the 0 padding that we were just discussing, which would result in, actually, it would result in this cycle over and over again. So BCD, BCD, BCD. Okay, so yeah, what we've done here in this trellis diagram is basically take the trellis from the above page and only highlight the paths corresponding to each data bit. So 0, 1, 0, 0, 1, 1, 0, 1, 0, 0, and then, as requested, 0 pad, 0 pad. Okay, so here is D, and here's our pad. It's much faster when the problem's already done for you. I remember doing this. It took me like 2 days. All right. So this, yeah, so this string 00, 11, 01, 01. Oh, here it is. The code word is what would then be sent to the channel coder. Okay, so this is only half the battle. We now would like to show that we can decode a received sequence, and that received sequence, we actually don't know whether it's going to have any errors in it or not. This is exciting. And so yeah, we're given the received sequence somewhere in the problem statement. And what I've done is I've chunked it up into pairs of bits because this is a 2-bit 2-to-1 encoder. So this is me zooming out a little bit. There we go. So we are told that the received bits follow this pattern 10, 01, 01, 00, 10, yada, yada, yada. And so let's build our Viterbi algorithm. So we're starting from a state that we know we have to start in. Then there is, which should not do orange. I think that's sufficiently different from the red and the blue. Both possible transitions from A require an error to be made. So that's why these both get a score. And remember, score is in golf, a score of 1. So 1 error had to have been made in the very first reception. We don't know which one it was because these are now both equally likely. We need to wait for more information. That's the whole idea behind Viterbi. If we were in state A at the second time step, then we would also require another error. So we should have encoded either 00 or 11, but we received differing bits. So that's why I'm going to add 1 on that, and I'm going to add one on that path as well. Because both of those journeys require one bit to have been flipped. If we were in state C and we received a 0, 1, that means 2 errors had to have been made. So that's why this 1 becomes a 3. Or if we were in state C and a 0, 1 was received, no errors were made along this path. So that's why that 1 becomes a 1 down there. And so now that we have multiple ways to get to every state, we need to do the comparison, or we need to store the least cost to go. So again, I'll work from top to bottom. If I am in state A and I receive a 0, 1, then that would mean adding 1 along this path. So that is the 1 that you see here. If I were going to end up in state A starting in state B, then I would require 1 bit in error. So that's the 1 you see here. So I'm taking the minimum of these two. And let's put it in green, that this is the preferred path. Right, this is the path that gave us the minimum cost. Right, that's the other thing you need to store when doing Viterbi, not just the cost, the minimum cost to have gotten there, but also the path that gave you that minimum cost. So let's see, let's do it for state B now. So I'm comparing, if I were to come from state C, that would mean 2-bit errors. If I were to come from state D, that would mean no bit errors, which means this is my least cost, which means that if I ever find myself in state B, given the reception that we received, I should have come from that direction. Right, that's the least cost direction. Same story in state C. The minimum cost would be this one, and then in state D, the minimum cost would be red. Okay, so the idea is, in the absence of ties, that there should only be one green path backwards from any state. So that once we travel backwards and we employ Bellman's principle, we'll have a unique path back to the maximum likelihood data word. Questions on this?
Why are we stopping in the middle of it necessarily? Is that just part of the, or would you go to the end? And I mean,
oh yeah, we got to keep going. We got to.
Okay.
This is like a 30-page solution set here.
Okay, okay. So you do go to the end, and then you kind of do all this.
Yeah, but yeah, I think the reason I stopped here is because this is the first time that we do this comparison. You're going to do this again for now every subsequent stage.
Oh, it's when you get multiple paths to this.
Yeah, multiple possible paths to a given state. Yeah.
Okay, that makes sense. Thank you.
Mm-hmm. All right. So scrolling. So here's the next stage. We're doing the same business. And then the 5th stage, same idea. And then I ran out of width on my paper. So actually, I wonder, now that this is all digital, can I do a little switcheroo here? Hey, look at that. So yeah, I mean, at this point in the decoding process, there is a pretty clear path, least cost path. So, but remember, we can only make these kind of concrete decisions once every data bit has cleared through the system. So we would do something like, to determine the first data bit, the first point in time that we could actually make that decision and not regret waiting for more information, I think would be here. So at this point in time, we could decide the maximum likelihood first data bit, right? Because one way to think about this is any time later, any stage later after this one, the first data bit is gone. It's out of the system. There is nothing in the system that corresponds to that data bit's memory. So we're not going to learn anything more about it. So we're not going to regret having decided what it was because we know we can't learn anything more about it. That's another way to think about that. Okay, what else we got here? I think we're back right side up. Cool. And so what you do if you keep track of what was the least cost path to get to every state is at the end of the day, Bellman says that the cheapest way to get to this state is to go from this state, and this is the least cost state that you want to be in. And then to get to this state, you want to have started from this state. And so what this can be used for is to say that the most likely data word is 1, followed by 0, followed by 0, followed by 0, followed by 1, followed by 1. Okay. And again, this is a maximum likelihood operation because at the end of the day, we are taking the smallest cost or the path that would have required the fewest number of errors is the same as the maximum likelihood decision. This is all predicated on a binary symmetric channel, non-burstiness of errors, and the fact that a hard decision is what has to be made. So at the end of the day, this convolutional decoder is going to output these string of bits, and then that's it. What you will see is that in capacity approaching codes, one way to approach this is not to keep a hard decision, but rather have a longer convolutional encoder, so more states, and then keep maybe not just the single cost to get to each state, but the cost, the 5 lowest costs to get to a given state, and then the scores associated with each of those. And so then instead of single numbers at each state, you can be treated as probability distributions. Like, I think it should be this path with probability 90%, but it could have been this path with probability 10%. And that's a way, it increases your memory, it increases the complexity of the algorithm, but it also is a way to not prune off branches that just appeared unlikely at first, but once you receive more data, become more likely. So that's it's called a soft decoding algorithm. Yeah, and I think that brings us to 2 o'clock. I think that also is this end of this problem, and so I will close with. I will close looking at you. Thank you very much for attending, or if you didn't attend, thanks for watching the videos asynchronously. I would ask you one more thing before you go, and that is to complete the course evaluation. I'm not claiming that the way that I ran this course was optimal, but the best way for me to improve on how to run the course is with feedback, honest feedback from y'all. So whatever you can say, good, bad, constructive, critical, I want to hear it. Yeah, I think I'll leave it there. I will post the final sometime tomorrow, and it will be due at 5 p.m. on the Wednesday following Thanksgiving. So you have, I think, about 8 days to work on it. All right. Thanks, everyone. Have a great holiday.